Hi there and welcome from Ventura, California to today's webinar, High Precision Application of UAVs, sponsored by ublox, InsideGNSS, and Inside Unmanned Systems, and hosted by WebAttract, the leader in thought leadership webinars. I'm Lori Dierman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session as our panelists continue the exploration of GNSS positioning, navigation, and guidance for UAVs. They'll be discussing use cases including high-fidelity modeling of vehicle motion, railway and pipeline mapping, as well as environmental monitoring. Note that you'll also have an opportunity to have your questions answered at midpoint and at the end of the presentation during the Ask the Expert session with all of our panelists. Now, we've invited you along with over 180 professionals from 54 countries and 29 states and provinces representing a variety of industries. And over the next 90 minutes, regardless of your industry segment or your location, we're confident that you'll find today's webinar of value. Before we get started today, Richard Fisher, Director of Business Development at InsideGNSS, would like to take just a moment to welcome you and introduce our sponsor as well as our main moderator for today. Over to you, Richard.
Thanks, Lori. Appreciate that. On behalf of the Inside Unmanned Systems and Inside GNSS team, including Glenn Gibbons and myself, I extend a very warm welcome to our international audience for today's web seminar. We're delighted you could join us. Our panel of experts will provide an introduction to real-time kinematic positioning, followed by presentations of real-world applications and benefit for UAV operations. In a short time, they'll take us from the theoretical to the very practical. And now I'd like to introduce our sponsor, Martin Strom of ublox. Martin?
Okay, thank you, Richard. So, hello everybody. My name is Morten Ström, and I'm representing ublox here today. It is, I must say, fantastic to see so many people joining. I guess that's what's going to happen when you have a good panel and combine that with two very hot topics, UAVs and high precision GNSS. We at ublox also find these topics interesting. UAV has become a very important market for us, where we closely follow the trends and try to capture the needs of the market. And in response to this, we have just launched NEO M8P, which is a small and energy efficient GNSS module capable of centimeter level accuracies. And with that said, I think we have some very interesting presentations coming our way today. I'm glad that we at ublox has been given the opportunity to sponsor this event. And let's go. I hand it over to you, Richard, to introduce today's moderator.
Thank you, Martin. I appreciate that. And I want to turn the webinar over to Demos Gebre-Egziaber. And over the years, Demos has helped develop and moderate many Inside GNSS webinars, and he is especially close to today's topic. Demos is an associate professor of aerospace engineering and mechanics at the University of Minnesota Twin Cities campus. His research deals with the design of multi-sensor navigation and attitude determination systems for aerospace vehicles. Recently, Demos' work is focused on multi-sensor solutions for operations in GNSS-stressed and GNSS-denied environments, including the use of such systems on unmanned vehicles. Demos, thank you for joining us again for today's event.
Thank you very much, Richard. Glad that all of you could join us this afternoon today for this very interesting topic on RTK and UAVs and high precision. With that, before we get started, let's take a quick poll. And Lori, if you could put the first poll up.
Absolutely. Coming up on your screen is that first poll. And we'd like to hear from each of you. For your small UAV operations, the centimeter level precision afforded by real-time kinematic, or RTK, GNSS it's absolutely necessary, an unnecessary luxury, too crude, perhaps not enough, or a myth. So looks like our front runner there, 71% coming in with an absolute necessity, 18% unnecessary luxury, 5% saying too crude, and 6% saying a myth. Demos, any thoughts there?
All right, so for the last three, unnecessary luxury, true, crude, and a myth, I hope today's presentations will actually change your mind on that because we have some really nice presentations showing you how RTK is really useful in UAV applications. With that, let me move over to introducing our first panelist here that will talk to us today, and that's Professor Steve Waslander, who's an associate professor in the Department of Mechanical and Mechatronics Engineering at the University of Waterloo in Ontario, Canada. He started his career as a control system analyst for Pratt & Whitney and then received his master's and PhD from Stanford University in Aeronautics and Astronautics. After joining the University of Waterloo in 2008, he founded the Waterloo Autonomous Vehicles Laboratory, or the WAVE Lab, where he works in the areas of autonomous aerial and ground vehicles, simultaneous localization and mapping, nonlinear estimation and control, and multi-vehicle systems. Steve?
Thanks so much for having me, Noah. So yeah, today I'm going to talk quite a bit about precise positioning for UAVs, and what we're going to do essentially is try to walk through the capabilities of these systems and how they relate to the applications that we're going to use them for. So starting off with the motivation, we see some beautiful examples here of data collected from different UAVs using both regular and RTK GPS solutions. So the first one we have is a 3D reconstruction of a large monument. Another one would be detailed inspection of transmission towers looking for corrosion. The third is an aerial view of agricultural fields looking at plant health, and then finally large-scale mapping of environments from the air. And in all these cases, essentially what we're doing is we're collecting visual or multispectral information from a distant viewpoint and trying to aggregate that information into a common view over a collection of images. And this process is significantly aided when you know exactly where the pictures were taken from or where the images were collected. And so the RTK GPS solutions that we'll be talking about today are a big step forward in getting that precise starting point and improving the output of the overall process. So my role today is really to go through the details of positioning and where the error sources come from in this process so that we can look at the benefits of going to these more complicated solutions. So going to the basics again, we're talking about GNSS, which is a satellite-based positioning system. And so we're receiving a range measurement to a receiver from the satellites that essentially measures the distance or the length of time that a signal travels through space in order to arrive at the receiver. And that true range that we're actually trying to measure is not what's actually measured by the receiver, of course. We measure a pseudo range, which is corrupted by a whole set of noise sources. The first being sources related to the satellite, so clock errors and position estimate errors. The second being related to the atmosphere, so ionospheric and tropospheric disturbances, and then finally those errors related to the receiver itself, so the receiver clock bias, the unknown position is what we're solving for, and then finally the measurement errors and multipath errors on the receiver itself. So when we put all those together, we end up with, and I apologize, I had to put at least a couple of equations in since I'm a faculty member. I got to keep teaching. So we'll have this one equation here to describe the nonlinear measurement model of a pseudo-range measurement. And so for satellite K to receiver U, the measurement equation is comprised of the following four pieces. First off, we have the actual range between the satellite and the receiver. Then we have the clock errors or distances, so the B for the bias on the receiver, and then the second term for the satellite error. We then have the atmospheric, so ionospheric and tropospheric errors, and finally multipath and other errors as well. And so the process of coming up with a position solution for a receiver is that of stacking multiple individual measurements from satellites and forming a nonlinear least squares estimation problem. And so we combine this set of pseudo-range measurements to form this estimate and simultaneously estimate the XYZ position and the clock bias on the receiver. We can of course augment this simple nonlinear least squares problem with temporal knowledge, so with some sort of knowledge of how the receiver is moving, especially if it's in a UAV where we have a fairly reasonable model of how the UAV will move. And we can also integrate additional measurement channels such as inertial and wheel odometry to further refine the solutions. So that if we stack up all the errors within the GPS system, and this is one particular example of a GNSS, obviously, we can look at what's called the user equivalent range error, so the individual contributions in error to the overall pseudo-range measurement. So for the civilian code, CA code of GPS, we get about plus or minus 3 meters of error simply from the signal arrival, from the measurement itself. And the more precise military code, the P code, has a tenfold improvement over the civilian code in terms of its measurement accuracy, so only 0.3 meters of error. Ionospheric effects for scale give you an error of about 5 meters. Ephemeris can add 2.5 meters of additional error. The satellite clocks add about 2 meters of additional error. Multipath can affect this URE by as much as a meter. And then finally, tropospheric effects are in the range of half a meter. And so when you aggregate all of these error sources and combine them in an RMS manner, you get a 6.7 meter error on an individual pseudo-range measurement. And then relating that through the position dilution of precision, you can come up with a position estimate, so a standard deviation for how reliable your current positioning solution is. So to improve on this stack of errors, essentially, there's many different procedures, but they all essentially try to eliminate those individual error sources. And so the first methods that we'll consider are the SBAS and PPP type methods. So SBAS is a satellite-based augmentation system, such as WAS or EGNOS in North America and Europe. And what these systems do essentially is collect information at a set of base stations with known locations that define a model for the ionospheric, tropospheric errors, the clock errors, and the ephemeris errors, and broadcast those over large regions that can then be received by the GPS receivers, and those errors can be removed. So this works well for the sort of large-scale errors that are well modeled from a finite set of base stations, but as you get to the tropospheric errors, which are local and rapidly varying, these models tend to have difficulty. And so the SBAS and PPP type methods tend to have limited overall maximum performance based on the quality with which they can predict and remove those error sources. So to get to the next level of accuracy, to get from the accuracies for PPP and SBAS down to the centimeter level, as we were describing in today's webinar, we need to move on to an additional technology, and that's known as carrier phase differential GPS. So the way this works is for a typical L1 code in the GPS constellation, the code itself has a wavelength of about 300 meters, and so an individual measurement in terms of resolution is capped based on that wavelength. But it is possible to actually track the position along the carrier wavelength as well, which has a maximum wavelength of 19 centimeters, and so therefore the resolution or the precision with which we can actually measure that range is significantly increased when we measure it along the carrier wavelength. The big challenge, of course, is that it's unclear how many wavelengths there are between the satellite and the receiver when you start talking about 19 centimeter wavelengths. And so my second equation is here. This is the carrier phase measurement equation. So we restate the same problem we had in the code phase solution. So once again, we have a pseudo range from satellite K to the receiver U, and that is dependent on the range between the satellite and the receiver. The same clock errors that we saw in the previous formulation, ionospheric and tropospheric effects are there again, and the multipath and measurement errors are included here as well. But we now have this additional term, this integer ambiguity, which literally defines the number of wavelengths between the satellite and the receiver. And this is a hard number to estimate. And so it leads to a technical challenge in terms of integer ambiguity resolution that's required in order to use carrier phase measurements. So how can we resolve this issue? We've got noise sources or error sources on the scale are significantly larger even than the actual wavelength of the carrier phase, and so it's actually quite challenging to try to use those measurements directly. And instead what we can do is we can use a differencing technique known as double differencing in order to remove all of those errors that are common between multiple measurement points and allow us to resolve the integers and then come up with a much more precise position relative to a base station. And so the way that works is for an individual single difference from one satellite, we'll have a base station and a UAV, and the difference between those two measurements will define a measurement of that baseline x u sub b. And if we do that twice for a second satellite as well, we can actually eliminate base clock errors, satellite errors, and ionospheric and tropospheric effects within the range of that base station where those errors are consistent between the two receivers. And so this leads us to methods called RTK and PPS, which take advantage of this double difference technique in order to come up with accurate estimates of the relative position. So what does RTK stand for? Well, RTK is a real-time kinematic GPS solution, and really what that means is that we're in real time estimating the relative position between the base station and the receiver, and we tend to use extended common filtering techniques for that real-time update. So to do this, of course, we need information from the base station, so we need to transmit that information from the base station to the receiver, and if that connection is lost, we have to revert to some other precise GPS method, so PPP or SBAS, in order to come up with estimates on board the vehicle of its motion relative to the base station. The alternative is to not worry about that real-time live link between the base station and the receiver, and instead to post-process all the information and apply these corrections offline to the positions measured. And so this only requires a base station to record its local measurements, and similarly the UAV as well. And so this eliminates the need for a live link between the base station and the UAV, but requires or doesn't allow or doesn't afford access to that high accuracy position during flight. And so essentially both of these are excellent options for GPS solutions for UAVs. It depends on whether or not you need that information in real time on board the vehicle for control purposes. So to stack up what we've talked about so far, basically we have all of the technologies in terms of the relative baselines for the differential methods and the accuracies that can result on this plot here. And so you can see that baseline GNSS system is on the order of 5 to 10 meters in error, whereas corrections when applied on the large scale, so both SBAS and PPP, can bring us down to 1 meter and to about 10 centimeters respectively. When we switch to differential solutions, we can see for differential GNSS, where we're working on the code phase between a base station and a receiver, we get roughly equivalent performance to SBAS out to about 1,000 kilometers of range. And the real winner here, or the really precise option, is RTK/PPK, where we can get down to centimeter level accuracy on 10-kilometer baselines and about 5 to 10 centimeter accuracy as we get out to 50-kilometer baselines. So in addition to this precise position solution of equal importance, particularly for UAVs with high variability in their orientation, is an estimate of the orientation of the camera system or the UAV itself when it's collecting the information that it's gathering. And so we've got a huge explosion here in terms of the types of devices that are now available, and a huge reduction in the costs of these systems and the accuracies for the same cost going forward. And of course these fall into two main categories. The first would be the MEMS devices, so these are accurate to about 1 to 3,000 degrees per hour depending on the quality, and these consist of gyroscopes, accelerometers, and magnetometers as you would find in your cell phone. These technologies are continuously improving and becoming more stable and more reliable in terms of their estimation, but there's a whole other level when we move into ring laser gyros and fiber optic gyroscopes in order to do the same measurements. So the ring laser gyros are a military grade device, and they directly measure the accumulated rotation, and fiber optic gyros tend to measure the orientation or the rate of change of orientation, but do it very accurately. And so with these two two technologies, you can significantly improve your orientation or your pointing accuracy in terms of using the information collected. And then finally, it's also possible to tightly couple GNSS and INS solutions into a single platform, and this can aid dramatically in tracking of satellites, integer ambiguity resolution, and the measurement fusion ultimately in estimation accuracy can be significantly improved as a result. So this leads me to the final summary, which is that we really see GNSS as the center of a large sensor fusion problem on board UAVs. So combining it with inertial measurement information and with map information in the operating environment is absolute measurement information, and all of this can be used to track the vehicle irrespective of what the vehicle sees in the environment. But we can, of course, also use ultrasonic radar, LiDAR, and vision or multispectral information to track the environment around us and also improve our position and orientation estimation. And so this fusion process that's now more and more being integrated into UAVs depends on two pieces, and that is first determining the individual validity of all the measurements, so whether or not they're currently useful measurements and properly capturing the state of the vehicle, and then finally combining all of those measurements so as to minimize the state uncertainty of the estimation process. And so with that, I'll pass it back to our moderator, and thanks for listening.
All right, thank you, Steve. So let's move on to our next panelist, and let me introduce him. Next panelist is Bastien Mancini, who started his career at CNES, the French space agency, in charge of trajectory and flight safety systems for the Ariane launcher, and he was in charge of the qualification for the Soyuz launch pad in French Guyana. After 7 years of work experience there, he left that and created Delair Tech with some friends that he knew from university. And the company was founded in 2011. Delair Tech grew to 50 people and was the first company in France to be granted the Beyond Visual Line of Sight certificate for operating the DT-18 fixed-wing mini UAV. He has worked in the development of ground control station, telecom, payload, and in charge of regulatory matters for Delair Tech and their UAV products. With that, Bastien?
Well, thanks very much, Demos, for the introduction. Thanks to ublox for inviting us to this presentation. So I'm going to show you a bit what we do at Delair Tech. We are a company that was created in 2011 in Toulouse. We are now about 50 people, and we have about 2 million euros of sales revenues. We developed our companies on developing fixed-wing UAVs for industrial applications. And now we've sold in about 30 to 35 countries our products. So our first product was this one. It's the DT-18, which was the first UAV to be granted Beyond Visual Line of Sight certificate in France and I think around the world. So it's a 2 kilograms fixed-wing UAV that can fly 100 kilometers, and it can fly for 2 hours. This plane has several options. It's initially designed to do inspections over pipelines, power lines, or other linear infrastructures, but it can also be used for topographic mapping, agriculture, monitoring. We will see this a bit later on. And so for precision topography, it has a PPK option, and we can also put a 3G or 4G modem into it to improve communications. After developing this product, we developed another one, the DT-26, which is just here, which is 15 kilograms and is designed to carry heavier payloads in order to have more quality data. And it's been used for surveillance, for example, by the French railway company. And it can be used also for monitoring or inspection or topography, but with bigger payloads, and therefore it can cover more area or with more quality. One feature which is interesting on that one for navigation people is that it's been financed by the French Ministry of Defense, and one thing that they have interest in is managing to use camera for navigation. So in case of lose of GNSS system, we use the camera to navigate with this plane. And after developing those two planes, actually, we realized that our customers had another problem. It was processing the data. So we've developed a third tool, which is called Dollar Analytics, and it can allow several kind of characters to work with our data. So there is a customer which can ask for a mission to be made. There is a pilot, and there are operators, people that can do quality checks or do some business analysis. Therefore, a customer can draw through an interface an area which he wants to be inspected or have a topography map or anything. The information is received by a pilot that can fly the UAV. Actually, the platform can also receive data from satellite imagery or plane imagery. All of the data is remotely processed, and there are some operators that, as I said, can do some quality check, also do some business analysis depending on the application, whether it be power line, agriculture, topography, or anything. And all the results are published to the customer. So now if we go a bit more into details on our PPK solution, we use a GNSS receiver, which is a dual band, and it's coupled tight with a high-end IMU. It's connected on board with an industrial global shutter camera, which gives very good quality imagery. And what's important there is that the time stamping is very precise, so it's less than 10 microseconds. And when you do operations like this on the ground, the pilot, what he needs to know is whether the data has been acquired correctly in real time. Therefore, the pictures are sent in real time by the global shutter camera to the ground control station, and the operator can see in real time the quality of the images. He can check the histograms in real time. He can see the footprint of each image to see if the area has been covered. And he also has on the top right corner quality check status of the PPK system. And therefore, the operator with this system has the real estimation in real time of the quality of the data acquired. We have also a solution that can send RTK corrections in real time through the 3G modem. But it's not the solution we put the first solution for us, because anyway the images have to be post-processed right now in order to have a topographic map. The images are post-processed in the Dollar Analytics platform, as I showed. Therefore, what's really important for the pilot in real time is knowing that the data is of good quality, but having the RTK is not really essential for our applications. And now if we go to the results of our data, for example, here in a typical data set, with our PPK solution, so we have for the GNSS receiver an accuracy of 6 to 9 millimeters in X, Y, Z on board. So that's the position of the mobile UAV. And now if we look at the accuracy of the results, which is an orthophoto or a digital terrain model, the absolute accuracy without any ground control point, only by checking checkpoints, is around 2 centimeters in X and Y and around 9 centimeters in Z. This very big accuracy, I mean very great accuracy, makes it irrelevant to use ground control points, and therefore the operations are faster. And also because we have an onboard IMU, very precise, we don't need to have a big lateral overlap, and therefore our system can cover bigger areas. It flies 2 hours, so it already can cover big areas. But by reducing the lateral overlap necessary to fly, we can really achieve great efficiency to do big missions that I will show in the next part of the presentation. And now I give it back to Demos.
All right, thank you, Bastian. All right, so right now we're going to take a pause here and allow you, the audience, to ask some questions of our panelists, and questions have been coming in, so keep them coming in. The first question is going to be for, I'm going to pose this to Martin. It's for you. And this question is, for these type of applications, would not PPP be better than RTK? Can you say anything about the two relative to the UAV application?
Yeah, okay. So Morten here. I think it's very application dependent which one you think is better or more elegant. They both have their pros and cons, definitely. The typical problems with PPP would be the long convergence times. That makes it a bit difficult to use in real-time applications. Hence, a local base station makes it can help you get around that such a convergence time problem. But indeed, PPP and kind of a state space representation SSR is something that we believe will come, and I think we will have products there in the future.
All right, thank you. Let's see, the next one is for Steve. It was a question about, I guess, your discussion about multipath, and you noted that multipath errors might be within plus or minus 1 meter. Isn't that a little bit too low, considering UAVs would be operating in urban areas, or was that, I mean, what was the assumption on that for UAV applications that you made?
The assumption there is that not all of the signals would be affected by multipath in the same way. So if only a single satellite is affected by a particular multipath reflection, then it can only affect the solution by up to a quarter wavelength, and so therefore it's limited in what its effect can be. But if yes, absolutely, if you're completely lost in an urban canyon, then those errors can grow more significant than that.
All right. All right, next one. This one is for Bastian. And the question is, can you say anything about what capabilities were required for the beyond line of sight operations?
Yes, so France issued a regulation in 2012 about this, and we had to make quite a big analysis describing all the failures that can happen on the system, the mitigation means we've put into it, and the failures can be of any kind. The analysis took several months with the French Civil Aviation Authority. They came to our company to do some tests and everything, and after that they gave the certificate. What's good for us is that our design is now certified by the French Civil Aviation Authority, and any operator who uses this design, therefore every time we produce a UAV, we certify that it's been produced in conformity with the design. Every operator who uses this UAV doesn't have to do the analysis again. It's been done once, it's certified, and this is how it works now.
All right, thank you. Let's see. Next question is going to be for Francois Gervais, who I have not introduced. He's going to be presenting the second half of this webinar, but the question is more appropriate for him, so I'll ask the question. Someone is asking that they have some photogrammetry projects with sub-centimeter accuracy required. How can we trust RTK data without ground control points? I think Bastian said something about it, but if you can add to that, Francois.
Yes, thank you. Thank you for the question. Yeah, sub-centimeter accuracy is something that is quite difficult to achieve even with a static GPS, static GNSS. So in RTK won't really help here. I might imagine that maybe there is a confusion between accuracy and resolution. If you do photogrammetry with millimeter resolution, RTK will help a lot to locate the project to a few centimeter accuracy to do the absolute accuracy to the absolute accuracy of the project. But sub-centimeter accuracy for RTK is just cannot be achieved right now.
All right. Let's see, next question for Steve, and it's about inertial measurement units used on UAVs. Can you say anything about the quality that you normally see on these and what's fused with RTK, quality of the IMUs or an INS solution?
Again, entirely dependent on the type of platform you're working with. For the most part, it tends to be MEMS related, just to keep costs down. But there certainly are excellent RTK INS combinations that are using the higher end solutions. The size of the platform also matters significantly here, in that the ring laser and fiber optic gyros are significantly larger than the MEMS solutions. So what kind of accuracies are we seeing out of the orientation estimates? Often about a degree or two on a nominal inertial measurement unit for UAV, and then improving beyond that as you integrate it tightly with RTK and use higher end products.
By the way, I meant to have Bastian make a comment about the previous question regarding centimeter level accuracy and ground control points. So Bastian, can you say something about that?
Yes, something that has to be taken into account is that our systems take images, and we have fixed-wing UAVs, Sensefly and Delertec, and they fly at typical speeds of 15 meters per second. And the cameras have an exposure time of typically 1 millisecond, and therefore, if you do look at this, the UAV moves of around 1 centimeter in 1 millisecond, and therefore going under 1 centimeter accuracy is quite difficult for this kind of systems.
All right. So the questions are coming in. Thank you very much, audience. Keep on coming in. We're going to have a second Q&A at the end of the webinar. So we'll get to those questions that we haven't got to right now. But I think we need to move on to the second half of the webinar. So let's do that. So Laurie, if you could bring up the second poll.
Sure can. So on your screen there, second poll question. Primary demand for RTK's performance in small UAV applications comes from, please select one of the following: precision agriculture users, construction industry users, mining industry users, mapping and surveying, or infrastructure inspection. Okay, looks like we have 10% saying precision agriculture users, 6% say construction industry users, 2% mining industry users, 66% mapping and surveying, and 15% infrastructure inspection. Any thoughts on these responses, Demos?
All right. Again, I guess mapping and surveying is where most folks think that RTK is going to be useful, but there are other places where it's going to be very useful. And the second half of Bastian's presentation is going to give us a little bit of a flavor of the different applications of RTK and UAVs. So with that, let me hand it back to you, Bastian.
Okay, thank you. So yes, now I will describe you a few applications that we've been doing. So with our systems, for example, here in Italy, there is a old mining site which has frequent landslide, and the European Commission, within the Copernicus program, asked our systems actually to fly over this area every 2 months. And in this case, the flights are about 10 square kilometers. It's made in 2 flights, and we get an accuracy of 10 centimeters, and we measure the movements of the land and the holes that happen because of the former mining site. A use case which was quite interesting was in Niger, in Africa. About 2 years ago, our TT-18 was used to survey railroad construction. So we did all the mapping of an area that was 150 kilometers long by 400 meters width, and it was made in 18 flights. It took 4 days to do the acquisition, but it was much cheaper than the planes. Actually, the customer who asked us to do this first asked a plane company, an airplane company, but it was complicated to get the plane there. So it was very quick to do with the UAV, and we reached the accuracy they needed to be able to draw the track. And it's quite nice because this railway has been finished to be constructed, I think, 2 weeks ago, and it's been inaugurated between Niamey and Dosso. And it was a nice job. Another application is for power lines. So in this case, it's a bit more complicated. The UAV flies over the power line infrastructure, and we do a 3D model of everything that's around the power line, and we also do a 3D model of the power line itself. It has to be very precise because the accuracy which is searched here is less than 1 meter, and what is looked for is the distances between trees and power lines. And after doing all this model and measuring it with the UAV, we do this risk map. So here it's a little movie showing it in 3D, but what we provide to the customer actually is this image, which is published on the Delaware Analytics website. So you see it's a risk map with areas with different colors that tell the customer where he has to go and cut the trees. And so we do this for thousands of kilometers in France, and now we are working on expanding this worldwide, abroad. Another application is for pipelines. So in France, the companies that manage the pipelines have a legal obligation to make sure that there are no vehicles that can dig into the pipelines to avoid the risk, collision risks. And therefore the UAV flies over the pipelines, take pictures, and we stitch the pictures together, make ortho photos, and then with the Delaware Analytics tool, we detect the vehicles automatically and again provide a risk map to the customer. And then with the DT26, we have some gimbal cameras that allow to do some surveillance. For example, in this case, tracking the vehicle automatically. So it's a video tracking. The operator says, I want this object to stay in the center of the image, and the UAV moves and the gimbal moves automatically in order to track the vehicle all the time. This tool can also have a night vision camera, and therefore it can be used for a night surveillance. And just to show you the accuracy of the system, this is at almost 800 meters, so we can see the people, and we can get at around 1 kilometer, summing all the errors. So that includes the GPS on board the UAV, the IMU on board the UAV, but also the gyros on board the gimbal, precision of the position of the objects in the image of about 20 meters in real time at 1 kilometer distance. And this is an example of stabilization in real time of the video also in the surveillance application, because when you have a great zoom, the image moves a bit, and so we have some software that can stabilize the image. But maybe with the stream rate, you cannot see really it in a very fluid manner. But the movie will be provided after the webinar, so you can download it and see how it works. And then another application is for forestry management. So this was done in Brazil, and the DT18 was used to measure the digital surface model of the terrain. We also deduced a digital terrain model, so that's the difference between the ground and the height of the trees. And making the difference between them, we managed to estimate the height of the trees on this area, which is exploited by a company that produces trees and wood. And you can see on the left of the image, the colors are the heights of the trees estimated by our system. So you see, for example, in orange, the trees that are 20 meters high. And this is displayed on the map. And this helps the company to estimate the percentage of trees of wood they will have in the culture. Another application in agriculture is using near-infrared bandwidth. We can estimate the growth of the culture, of the crop, of the corn or anything. Well, not anything, but some of the cereals. And with that, thanks to that, we can deduce and give advice to the agriculture people of how much fertilizer they should put in their culture. And for seed companies, here's an example of what we do. They do many. They try different seeds, and they have what's called microparcels, and we can count automatically the number of plants that have grown in each microparcel. And here there is a coding color that says how many are on each of them. And with this, they know which are the best seeds and what they will sell in the market in the future. Coming next with our systems are LiDAR on the DT26, the Regal one, which is 4 kilograms, and a hyperspectral camera. Both these sensors are linear sensors, and therefore they need high accuracy GNSS receiver and high accuracy IMU. This is just an example to show that we use the one on the right, the 5 megapixel camera, and not the 20 megapixel consumer camera, because we only use industrial products in our systems. We work for industrial customers, and what they need is quality. And therefore, that's why we use ublox GNSS in our systems. They are reliable, they give good results. Nobody asks the quality of the results of these sensors. And our industrial customers who are here, they're just expecting quality and measurement, and not only things for to be nice, but they really want measurements for industrial applications. And that's it, and I give it back to Demos.
All right, thank you, Bastien. All right, so our next panelist is going to be Francois Gervais, who is a geomatics engineer and has worked for Leica Geosystems and as a professor at the Technical University of Applied Sciences, Western Switzerland. In 2010, he launched Project RPOD, a photogrammetry on-demand project, before founding Easy2Map, a drone-based photogrammetry service provider in 2012. Francois joined SenseFly in February 2016, and he's also the president of the Swiss Photogrammetry and Remote Sensing Society. With that, I will give it to you, Francois.
Okay, thank you, Demos, for the introduction, and thank you for the invitation. First, a few words about SenseFly. So it is now it's no more a startup. In Swiss terms, it's more than 120 people and selling between 100 and 200 units a month. And we have a full range of products with the well-known fixed-wing EB in 3 different versions, and a relatively new multi-rotor called EXOM. And both platforms are controlled with the same software, the eMotion software. Well, what is different in EB RTK compared to the standalone EB? First, you have a RTK-capable GNSS antenna, GPS and GLONASS on both frequencies, L1, L2, and the geotag that will be produced during the flight are much more accurate than in the standalone version. The eMotion has the ability to receive correction from the base station or from a VRS, so virtual reference station. And it includes as well a bit of post-processing only if needed when the base station is located on an unknown location. In the end, the accuracy is about 2 centimeters in horizontal and 3 centimeters vertical. The goal is always to keep the accuracy in the range of 1 to 3 times the GSD, and all that without ground control point. Now let's take a look at the short video showing how it works in the field. So we have here a typical surveyor preparing the EB, and at the same time preparing the base station. Again, it could be on a known point or an unknown point. The system is almost ready for takeoff, and it will be launched by hand, and the there is here a few comments that you will be able to hear in the video that will be posted later today. Very shortly, there will be the landing and the control with the emotion. Here we compare the different scenarios that I will repeat later, but the base station can be a real one or virtual one, and if real, it could be on a known location or it could be on an unknown location. If the location is unknown, the geotags will be computed in real time. They will be they will be approximate, and they will be fine-tuned after the flight with a little of post-processing. And here we have a nice view with the antenna, the GNSS antenna, and we can switch to the next slide. Voila. So from the upper left in the counterclockwise rotation, you have the standalone situation with just DEB and a modem for controlling and some feedback from the drone. In the second scenario, with the local base station on a known point, the base station will transmit the information to Emotion, and Emotion, the software, will transmit with the same modem to the drone, will compute the correction, and will transmit the precise position to the drone. In the third scenario, bottom right, the base station is on the unknown location. The geotag or the RTK correction and the geotag will be less or approximate, and they will be refined later. And in the fourth scenario, the upper right one, it will work with a virtual reference station, so no base station, just a GSM communication with the RTK correction available in many countries. So the question is, okay, why do I need RTK? And the answer can be given here in 4 points. The accuracy of the GNSS is guaranteed in the field, and actually you can guarantee, you have an indication of the accuracy of your geotag before the flight. So you will start the flight only when the little OK that you can see here says, okay, now you have the highest accuracy. Another point is you don't need additional software. It's the same Emotion. You will just need to connect your existing base station or VRS, it's a virtual reference station service. So it's the same software like for the standalone. No additional work on the ground or in the software, and much less work on the ground regarding a ground control point. And the good thing is, when you get back to, before returning to the office or on the way back, you know that your job is done and that your geotag are accurate, and you will have a fine processing later. So for these 4 reasons, there is no question about is RTK a need or not. Now that the context is explained, let's get to some accuracy assessment, and I could only suggest to take a look to this white paper explaining the procedure. So we were on a small area, 0.2 square kilometer, and with the VRS virtual reference station, the Swiss service SWIPOS. No ground control point, only checkpoints, 19 checkpoints in this area. And we would just have so 2 flights in 2 very different conditions. In the first case, ideal condition, sunny, no wind, low flight, 2.5 centimeter GSD, And in the second case, adverse condition, bad lightning, wind, and flying a little higher for 5 centimeter GSD. And what are the results of this procedure? In the ideal situation, almost the same number like Bastian mentioned before. We are in the 3 centimeters horizontal and vertical in the 3 centimeter range. This is for the point cloud, and almost the same for the orthomosaic and the digital surface model in this chart here. Interesting is in this perfect condition, we remove 10% of the geotag just to see if we have an uplink lost or some missing geotag or less accurate geotag in our block, and we can see that it goes slightly higher in Z, but the accuracy, the block accuracy remain in the standard or in the expected accuracy. In the adverse condition, of course, the accuracy get a little bit lower, but we are still in this 1 to 3 times GSD, and we are well below the 10 centimeter accuracy, is it in horizontal or in vertical. So it sounds very good. So we can now check 2 projects here produced by our customers or users. And the first project is a long corridor, a 250 kilometer corridor in Australia. And corridor mapping is always a problem because it typically requires a lot of ground control point. And in this case, with these requirements, it could have been very difficult. And actually, the whole project could be done in 15 kilometer sections. So the team was able to move quite fast along this corridor, and on only 3 existing real ground control point, the whole project could be done. The second example is another corridor, quite long as well, 30 miles in California, the high-speed railroad. And what is really interesting is the statement at the end of the job, so that the job could be completed in the quarter of the time compared to a terrestrial method, and half of the cost of a manned aerial service. So less time spent on the ground, less money spent, and the whole project could be flown. We can see here some numbers with a staff of 6 people, and you can see the requirement in terms of accurate of ground sampling distance was very high, or 2 centimeters, and everything was done in 4 weeks, quite nicely for this first project. And since the same company has done more projects with RTKs with the same success. And we come to the summary here, and to summarize the 3 reasons to go for RTK. First, you can use your existing base station and make the connection with the drone for this and get these accurate geotags. The workflow is fully integrated. It means the software remains the same, the drone is the same like the one that you will use for standalone missions, and you can still do standalone mission with this drone. So no additional software, no additional work in the office, and the final result is you get on the spot, immediately in the field, you get the survey grade accuracy of few centimeters and the guarantee that you are below 10 centimeters at any time. And this is my conclusion, and I give you back, get back to demos.
All right. So thank you. Yes, we're having a lag on the view graphs. All right. think we're good. We're there now. All right, so let's see some next steps here. So the PDF version of this presentation will be on the InsideGNSS website, and a recorded version of it will be available as well. And we've given you also some contact information for InsideGNSS and ublox, and if you want to go and see more information on products and this webinar. All right, so with that, let's go to the first question, and this one's going to be for you, Steve, and it's about, and if the others want to say something later on after Steve does, you can. How does camera quality influence the precision on the ground? You know, why is the quality on adverse conditions such as the, you know, things like not the perfect day, etc.? How does that play into the this problem?
Sure, yeah, I'll start this, but clearly we've seen some good examples in the field of the difference between clean conditions and adverse. Essentially what's happening in terms of camera quality is the number of pixels per meter of area covered. So the lower quality the camera is, the closer you need to be to get the same resolution on the ground, and the more precisely you actually measure the information or the light that's coming off of that patch of ground. So obviously camera quality can help significantly in terms of improving the overall results. The adverse conditions, that lends itself to issues with lighting and issues with tracking of the motion of the vehicle, and so in both cases those can also degrade performance.
All right, Bastien or Francois, do you want to add anything to that?
Yes, well, about the camera quality, indeed, it's very important, and that's why I put a little slide about our 5 megapixel camera. So it's 5 megapixels today, nowadays looks like a small figure. However, what's important in our case is to have a big pixel pitch. So every pixel is big, and therefore we can have a very short exposure time, and therefore the image is not affected by the movements, the dynamics of the flight. And even in adverse low light conditions, we can have a short exposure time, which is very important for dynamic systems like ours. So we can typically go down to 1 of 10 thousandths of a second for exposure time. And indeed, with cheaper cameras, they can be rolling shutter, and also they have usually much smaller pixel pitch, around 1 micrometer for the pixel pitch, and 1 to 2, and therefore, even though they have many pixels, the whole quality is very low.
All right, Francois, anything you want to add on to that, or
yeah,
do you think you covered it?
No, I could only agree with what was said. The quality of the whole mission will be only as good as the weakest link or the weakest component in the procedure. And today we talk about positioning and very high quality positioning. If the camera is not as good as this, then the whole thing will be a bit lost. So yeah, it could be the subject of another webinar. Totally agree. Camera quality is a must as well.
All right. All right. Let's see. So this one is for you, Francois. It's why is the corrections in what you showed not sent directly to the drone, but via the emotion software? What's the logic for that, or what was the explanation for that?
The first aspect was to keep the whole procedure simple for the user. So is used to emotion, and emotion was ready to get the correction from any base station. Is it a real or virtual one? And we had this connection, this modem connection at 2.4 gigahertz that was available for uplink and downlink, and it was just very convenient, and it was technically possible to send these correction via emotion to the drone, and it's just a convenience, and it just for the comfort of the user.
All right. Let's see. All right. Next question. This one is for you, Steve, and it's how do you calibrate navigation sensors in the imaging component in order to get the best overall system calibration, including the camera itself? And again, if afterwards, Bastien or Francois might want to say something about that. They can.
Sure, yeah. So particularly for the camera, we always start with intrinsic calibration based on a checkerboard or a large pattern that eliminates a lot of the errors and defines the projection matrix for points in the image plane. To calibrate relative to the GPS, we tend to do it mostly with a tape measure on the platforms that we've worked on. But of course, you can refine this through various estimation techniques for that that particular baseline. And so I'd be curious to hear from our other panelists what procedures they use on their platform specifically.
Yeah, if I can add something, sorry, Bastien. We are lucky enough that on drones, all the distances are very short. We have the help of the IMU or the MEMS. So when all the geometry is quite easy to handle, and if we can easily go down to the millimeter or maybe 2 or 3 millimeter level, is it on the ground or in air with turbulences and so on.
Yes, and on our side, so the interior parameters of the cameras are obtained through calibration before putting the camera into the UAV, and then they are recalculated in the photogrammetry process. The level arms parameters are known through the CAD design. So that's the relative position between IMU, GNSS receiver, and camera. And the bore sight angles are not measured, but are calculated in the photogrammetric process.
All right. All right, so let's see. Next one is for you, Bastien. How important is LiDAR for the inspection of power lines and making the digital models of what the example he showed?
So LiDAR is very important because with the DT18, so the small one, it's only 2 kilograms, it cannot carry a LiDAR. What we do is photogrammetry, and photogrammetry we cannot measure the position of the power line. We do a model thanks to the data that is provided by the camera. So whether it's been measured by a LiDAR or they give us the tension parameters, the width of the line, the name of the pole, so we know where the line started and where it goes. And we do a 3D model of the line, but we don't measure it. And therefore, the maps we have the accuracy they need, but the power line is not measured itself. With the LiDAR, you can measure directly the position of the power line. You can also see the ground through vegetation, and therefore you have in the same measurement the ground, the top of the vegetation, and the power line, and that's very useful for these applications.
Right. Anything any of the panelists want to add to that, Francois or Steve? Yes. All right. Don't have to. All right. All right. Let's see. The next one. Let's see. This question is going to be for Steve, and the others could also pipe in. It's asking of algorithms or software used for combining all this information. Are Kalman filters necessary? Are there other types of software that can be used?
My take on this would be that the Kalman filter, and specifically the extended version for nonlinear systems, is pretty much the default starting point for sensor fusion. It just naturally fuses multiple measurement sources and prior information in a consistent manner. The things you have to be careful with Kalman filters, of course, are that the information going in is consistent, or not corrupted in any way, in that it's quadratic formulation and therefore very sensitive to outliers. And so particularly in my area of research, where we use vision points for localization, we have a lot of trouble with this correspondence problem, or this consistency of the measurements being used. But that would be the dominant way I would suggest. Particle filters is another option as sort of a non-parametric representation, but these are computationally quite expensive and tend to scale poorly with the size of the solution space.
Okay. Any other comments from Bastien, Martin, or Francois?
Yes, it's Francois speaking.
Okay.
Yeah, I can only agree. And the other thing is I would say the quality of the measurements that we have today, is it GNSS measurement, I mean, the signal to noise, or is it from the MEMS? The quality is much higher than what we had like 10 years or 15 years ago, when we were doing this direct georeferencing, and where the computation was I mean, first the performance of the board, of the real-time board was lower, and the signal to noise was much lower than today. So we are lucky enough that all the hardware and the software are now much better than 10-15 years ago.
Okay. All right, so let's see, next question. I will pose this one to you, Francois, and it's someone talking about the experience they had about making orthomosaic maps, and I'm assuming this is on the US side, because they're limited to fly in areas, forested areas, where they can't fly above 400 feet AGL. How could RTK help resolve computing, forming this orthomosaic map? How does RTK help in that? How would RTK help in that problem?
Yeah, it's a well-known problem. This flying over forested areas. Ideally, you want to fly higher, and all the bundlers will work better, but you cannot. So the RTK will help in this case, but make sure that the software that is used, the bundler that is used for later in the process to bundle the images together, that this software is able to handle this accurate geotag. And here at Sensely, we used Pix4D. We mainly used the Pix4D software, and this was the fine-tuning when we had this accurate, centimeter-accurate geotag, how to make sure that they are used at their full potential. And we are now we have this streamlined workflow, but it wasn't easy. And there are not so many software that will rely much more on the geotag and less on the content of the image. And this is the trick: rely on the geotags and less on the image.
All right. Next question is for you, Bastian, and it was a comment about the endurance, or the length of time. You talked about the UAV was able to stay in the air. So it's 2 hours, you said, and one of our audience members is very impressed by that and wants to know, how do you do that? Or can you say?
We worked hard on it. What can I say is maybe I think many of UAV people have a culture of robotics. We are created in Toulouse, and Toulouse is the town of Airbus, and we have quite a strong culture of airplanes, aerodynamics. The engineering school to go and work at Airbus, we are just next to our office, and we work with them often. We do some how do you call that, wind tunnel test of our systems. So I think it's mainly cultural. We are in a place where we have the people who can do that. And also it was something that was necessary for us from the beginning, because when we created the company, two of the founders were working for oil and gas companies and were looking for an automatic system to go and make images at least 50 kilometers where they needed to go and see the problems. And in France, the regulation said if you are less than 2 kilograms, you can fly however far as you want. So we designed actually something less than 2 kilograms that can fly as far as possible. And the result was the TT-18.
All right. So maybe I should ask a question. So in other words, the vehicle was designed from the get-go to be a long endurance vehicle. So
yeah,
is that correct? Okay. All right. Good. All right. Next one. I guess this is for everyone, but I'll start with Steve and then go to Martin and down the road. What are the benefits of L1, L2, L1 only, and the future, I guess, of L5 coming in with RTK for the UAV applications?
Yeah, so the short answer is the more frequencies, the better. Essentially, we can eliminate some of the noise sources within those pseudo-range measurements by comparing signals received from the same satellite on different frequencies. So L1, L2 is significantly more reliable in terms of being able to remove some of the necessary measurements. It also helps dramatically on integer ambiguity resolution. Having this multiple channels, you can actually resolve the integers more rapidly. So in both senses, it helps speed up the and improve the availability of the RTK solutions. So L1 works, but it can take quite a while to recover a solution. L1, L2 is a huge advantage, particularly for RTK, and then adding on L5 can only be better, right?
All right, Martin, would you want to add anything to that about?
Yeah, I can just conclude what Stephen just said. It is, but I maybe could stress that because this is a question we hear ever so often. It's not the accuracy when you put them next to each other. It's not so much the accuracy. It's not there where you see the differentiator, but it's the availability under what circumstances we can reach these centimeter level accuracies. And here, with a dual band receiver, you typically will be able to work with longer baselines, for example, but with short baselines, the accuracies that you'd get would be the same. That's not the differentiator, but as Stephen said the availability.
Okay. Francois, do you want to add anything to that, or do you think they got it all?
Yeah, it was perfect. I could just add a bit of history. When I remember in 1996, we were already trying to fix ambiguities with L1 only, and it was really a challenge. And then came L2 with a lot of noise, and then it's always a question of signal to noise. And as Steve mentioned, if L5 can help us, it will be even easier. It means we can go in even more difficult situation, and we will have this high accuracy available more often, actually.
All right. Well, this one's for you, Francois. I have you here. It's a question about the RTK EB, our non-RTK version of it. How easy is it to convert from one to the other?
It's an interesting technical and commercial question. Yes, it's possible to. I mean, it's the same airframe. It's not. I mean, the board is different, and you could see on the video that there is the little. You can see the GNSS antenna, which is slightly bigger, of course. I mean, going from code to phase means a different antenna, but there is an upgrade path. But then it's no more a technical question; it's more commercial question, and I think it's not the place to discuss it.
Okay. All right. Let's see. Next question. This one is for you, Steve, and I guess after you do them, maybe Bastian could also chime in. Antenna-specific errors, are they important for these low-cost RTK systems, and what are they? How do you deal with them? How do you have to count? Would you account for them, and so on and so forth? Can you say something about them?
I don't have too much experience with the antenna errors themselves, but yes, they certainly do influence the measurement process. So we've had a lot of experimentation go on in the lab to try to identify errors, antennas that worked well with particular solutions. And so from our perspective as roboticists, is really a bit of trial and error. But I think having these commercially available products is a nice step forward where these problems have been resolved for you.
Bastian, do you have anything that you want to add to that?
Nothing very relevant, but indeed it's a very important object in the chain, and we've also had some trial and error. It took us some time to find the good antennas, finding the correct position of the antenna also, because these systems are quite small. There are some high frequency CPUs on board. There is a lot of electromagnetic issues, and finding the correct antenna is a tough task. But once you have it, it's okay.
Yeah, I'd also say that selecting a good antenna and placing it is very important for it's critical for the success. But having said that, people depending on the background, I can have very different views of what is a quote good antenna, depending on the background. So we at ublox we serve a broad market of various customers, consumer end products, wearables, and if we talk with people from that end, for sure we must point out to them that they cannot compromise the antenna design. They must. Once you go into RTK and carrier phase tracking, you cannot compromise on the antenna design too much. But having said that, also coming from the other end, there are good and affordable single frequency patch antennas that are up for the job. You don't have to think that this is overwhelming, too expensive. It is, but it is an issue that you should take care of and spend some time making the right choices.
All right. All right. Let's see. This question is going to be for Francois, and one of the audience members is asking, why was RTK really necessary for the applications you showed? Couldn't you have as well done it with raw GPS or something else? So
it's interesting. Yeah, it's interesting. Of course, just to do the flight, I mean, the code will be enough, and this is what happened with a standalone solution. And you have an accuracy of a few meters, and it's perfect for the guidance of the drone, and just to do the flight plan as planned. Then, okay, you could record the phase and process it later. It's possible. Why is RTK interesting here is that as soon as you land, you don't have to process anything. You are not going. You are in a remote area. You are not going to process any image or whatsoever. But as soon as you land, you have the guarantee that your geotags are accurate, and then there is no additional post-processing. So here again, the accuracy that you get eventually after all the processing, we both with Bastien demonstrated you get something that is what you get normally. The interesting point is you know that you have this accuracy much earlier in the process, and in this case, in the field, before going for the next flight, you already know that you have your accurate geotag. This is the reason why we would prefer and we would suggest RTK in these two projects.
Okay. Bastien, would you want to add anything to that, or do you think Francois got it all?
No, I think Francois got it all.
Okay, good. All right, so let's see. It looks like we have time for one short question, so I'll direct this one to you, Martin. How RTK and platform dynamics, UAVs tend to move and jostle around a lot. Anything you can say about how robust it is to being installed on UAVs and used for these applications?
Every application has its challenges, and maybe the UAVs they are maybe not so challenging. They have typically a very good sky view, so RTK is quite well fitted for UAVs, and also the dynamics is not so dramatic compared to other places where people would like to apply this RTK. But maybe then it would be to Francois or Bastien to for example, comment on problems coming from vibration and other sensors going on the UAVs, if you have experience of that.
Francois, Bastian, quick comment.
Okay, yeah, yeah. The challenge, I think, in terms of the accuracy that we get is good enough. It's quite clear. You mentioned before the variability of this accuracy. You want to be close to 100% of the time do you have this accuracy, and this is the challenge. And the other challenge is the small size of everything. I mean, we mentioned all the electronics that is in a very small area, very small volume. And the other fact is the cost. I mean, the financial point of view, we add more sensors and we want to keep the cost very low. So we are happy to have inexpensive sensors that can be integrated and gain this higher accuracy at reasonable cost.
All right. Well, unfortunately, we got a lot more questions, but the time is up and we have to call it quits here. So thank you for being with us, and I will hand it over to you, Lori.
Absolutely. It is about that time to wrap up. First, however, a few closing remarks from Martin Strom of ublox, our sponsor. Martin?
Okay, once again, thank you to InsideGNSS and Inside Unmanned Systems for making this happen and for giving us the opportunity to sponsor. And a big thank you to all of you in the panel, Steve, Bastian, and Francois, and of course to everybody that spent 1.5 hours with us here to the very end. Thank you very much for your attention, and wish you all the best in your projects and yeah. And some final words from you, Laurie, before we end.
Absolutely, and thank you, Martin Strom and folks at ublox for sponsoring today. And once again, thank you for joining us. This is Laurie Dearman saying, hope we see you on the next one. Have a great rest of the week. Bye for now.